Hi, everybody. We're continuing our discussion of indexed sets, and we're turning our attention to sort of the main reason that we look at indexed sets, and that is, what if we have not just 3 sets or 5 sets or 10 sets, but what if we have infinitely many sets that we want to deal with all at once? And this is where the power of the indexing really comes in handy for us. So let's go ahead and look at, this is example number 2 in today's handout. And it says the following. Consider the following list of sets. So the first one, A1, well, that's equal to a set containing the numbers -1, 0, and 1. Okay, then the next set, A2, that's equal to the set containing the numbers -2, 0, and 2. Notice that the size or the cardinality of A1 is 3. It has 3 elements. And the cardinality of A2 is also 3. It has 3 elements. Okay, A3 is a set that contains -3, 0, and 3. A4 is a set, of course, this just says ... but that ... notation, as I've said, it's the worst notation ever because it means the pattern continues. So let's just continue this pattern and make sure that we've got it. A4 is the set containing -4, 0, and 4. A5 is the set containing -5, 0, and 5. And then the ... continues, and the point is that this list is not done yet. We can keep going. In fact, we can go a lot farther than this. So if I gave you a number like, if we kept going A5, A6, A7, A8, A9, A10, up to A20, let's say, A20 would be the set containing the number 20, the number -20, the number 0, and the number 20. And the set A117 is the set containing -117, 0, and 117. And ... it keeps going. Now, how many of these sets are there? Well, it keeps going ... at the end, which means that as far as you can count, you're going to get these sets. There is one of these sets for every natural number. 1, 2, 3, 4, 5, 6, 7, 8, ... on forever. And that means that there are infinitely many of these sets altogether. And what we're interested in doing, maybe just as a note, this last notation here, this tells you how to build one of these sets. If I give you a number I, and I say, give me the ith set, so for example, give me the 1000th set, this tells you how to build it. It says put in I here and here, so negative, and then if I is 1000, if this is the 1000 set, you'll get -1000, 0, and then 1000 in your set. So this is a little bit like a formula or recipe for building each one of these sets. It's sort of a way of explicitly saying what all of these sets look like so that you don't have to rely just on your pattern matching for that to fill in that ... Okay. So let's go ahead and talk about the union of these and then the intersection. So for the union of these sets, this is the union, we're going to say I equal 1, and then up to, well, we want to go all the way up to infinity, so we go like that. I equal 1 to infinity of AI. And what does that mean? Well, it just means that we do A1, union A2, union A3, union A4, union ... and those unions just continue on forever. And what does that union end up looking like? Well, it's a set. And what goes in there? What goes into the union is anything that's in any of the sets along the way. So in particular, we'd better put these things into that union, -1, 0, and 1. We'd better put in -2, 0, and 2, and -3, 0, and 3, and etc. So let's go ahead and start writing these. Let me see. I'll just blow it up so I have a little bit more room to work here. I'm going to write these like, I suppose we could do them like this, -1, 0, 1. And then we go to the next set and we put those things in, -2. 0 is here, but we've already got 0 in the set, and there's no need to put it in twice. Once you put it in once, it's okay, so I just put a 2. Then from the next set, A3, we're going to put in -3 and 3. And then from the next set, the 0 is already in there, so we don't have to put it in again. And then we have -4 and 4 and ... etc. If you look at this, you can tell that what's going to be inside is 0. And also all of the positive whole numbers, those are the natural numbers, 1 and 2 and 3 and 4, and on and on and on. And also all of the negative whole numbers, -1, -2, -3, -4. So you can write the set just as we did. That's a fine answer, but you could also write it like this. Might look slightly more familiar. Putting 0 in the middle, and then -1, -2, -3, and ... on this side, and 1, 2, 3, ... on this side. So this is another way of writing the same set, also perfectly acceptable. And this happens to be one of the sets that we have a name for. This set, which is all of the positive and all the negative whole numbers and 0, that collection altogether is called the integers, and it's denoted with this what's called Blackboard Bold Z. It's like a Z with an extra diagonal stroke in it. And it's called the integers. So when we take the union of all of these sets, what is that union equal to? Well, it's equal to Z, to the integers. The set containing 0, 1, 2, 3, ... and -1, -2, -3, ... all of those, infinitely many things. Okay. Now let's talk about the intersection. So intersection I equal 1 to infinity of AI. It's the same sets, that is, it's still these sets that we're intersecting. But remember that when you do intersections, the result of this intersection is going to be a set, and the set that you're going to get is the members of that set are going to be exactly the members that appear in every single one of these sets AI. Whatever members appear in here, they have to appear in A1, but also in A2, and also in A3, and also in A4. And if you look, you can see that the only number that actually appears in all of these is 0. 0 is in A1, A2, A3, A4, and A5. 1 is in A1, but it's not in A2, so we can't include 1 in the intersection. 2, same for -1. The numbers 2 and -2 are in A2, but they're not in any of the other A's, and that means that we can't include them in the intersection. So the intersection is just the set containing the number 0. Okay. So here we have, let me see, I'll just box my answers so we can see them. The union is equal to this set, or if you prefer to write it in shorthand, it's the Z. And the intersection is equal to the set containing just a single element, 0. The last thing that I wanted to point out, so we're done with this problem. The last thing I want to point out is just to consider in this problem, what is the index set? So we refer to the index set as I, that's the index set, and it's just a set containing all of the things that we used as indices. So in particular, it contains these numbers here that we use to label the sets. It contains 1, 2, 3, and ... which means it must contain 4 and 5 and 6. You can see if you write out all of these sets, there's one which has a 4 there and one which has a 5. If we kept going, you'd get one that has a 20 there and one that has 117 there. So there's a lot of stuff in this index set. The index set is the set 1, 2, 3, 4, 5, ... and it keeps going forever. This is a name for this set, also has a nice name. This is just called the natural numbers. The natural numbers are the numbers that go 1, 2, 3, 4, 5, ... So if I were to ask you in this problem, what is the index set? The index set in this case is the natural numbers, n. Okay, that is it for this example. In the next example, you're going to see what happens when we want to have an index set other than n. What other infinite index sets can we use, and what do we need to do to our notation here in order to indicate that we're talking about a different index set there? That's coming up in the next video. See you soon.